My name is Eric Schneider from Chariot Solutions, and I want to start talking about data lakes. So your organization knows what it's doing tactically, right? I see some looks in here. So I presume that it does because you're in business. So you're doing what you need to do with the data that's flowing in. So if we're talking about sensor data, and you have a business dealing with sensor data, you're sending out work crews when you detect leaks, or you're in part of a feedback loop. So you're seeing temperature changes, and you're talking back to your devices to be part of that feedback loop. But what are you doing strategically, right? So what do you do with all this data that's flowing in? And then how do you use it for analysis? And then how do you store it? That's what we're going to talk about. So what do we do with all this data? There's a lot of terms out there. Data warehouse, data lake, data puddle I made up, but feel free to use that. We're going to talk about Flink, and then we're going to talk about the AWS Data Lake solution. So let's get a little bit of perspective here. So this is just sort of a hypothetical, just to get an idea of the volumes of data that we're talking about. So let's say there's a business that has sensors in a hotel room, right? There's an average of 2 sensors in a hotel room. And each sensor sends a message every 4 seconds. Maybe that seems like a lot to you. If it does, then replace hotel room with factory. I know it doesn't really matter. And there's 256 bytes per event. So, maybe you have some sensor data, temperature data, flow rate for water or something like that, an ID, and maybe some account data. There's more than 5 million hotel rooms in the USA, so depending on the success of your venture, if you have just 0.5%, that's 1/4 of a terabyte per day. Well, I know that's a tebibyte, not a terabyte, but I don't know. I'm kind of old school, so I'll just call it a terabyte. 1% is 0.5 terabyte, and 5%, you'll have 2.5 terabytes of data per day. So this is fine for sensor data. Sensor data is kind of the perfect scenario. You're just talking about numbers. You're talking about some integers, maybe some booleans, some ranges of values. It's really easy to compress and for that data to flow efficiently. But most of you probably don't deal necessarily with data that looks that nice, right? So, let me go back to this. So what if you have data that's not so clean, right? So, you have some developers that tend to create, let's say, less than optimal data for you to consume, right? So let's call one of your team members Skippy. What if Skippy decides that we need to consume data that's, maybe it's nested, maybe it's complex, maybe it's more data than you need or want, maybe it's some crazy delimited pipe, comma, semicolon, key value store that he came up with. So oftentimes we have to deal with that data that's flowing in. So it ends up being a lot more than 2.5 terabytes per day. You could consume potentially, hundreds, millions, trillions of events per day. So what do you do with it? So Keith kind of touched on this, right? So we have time series databases. That's perfect for anything that's queried within time ranges. If you need to aggregate, do whatever operations, sums, averages, means, evaluations on time series related data. It's ideal when time is primary. So sensor data, that's perfect for that. But a lot of our data isn't necessarily like that, right? It's facts that you need to aggregate or query on or select later. So time series isn't always an option. Old school relational, as Keith mentioned, relational systems in response to pressure are scaling up and out better than ever before. You can have relational tables with hundreds of millions of rows, and it works fairly well. Relational warehouses, Amazon Redshift. There's a lot of I don't want to say necessarily, well, I guess there really are proprietary solutions where it's sort of magical. You put the data in the data warehouse, and it sort of knows the right way to store it, and it knows how to query it, and it just, it basically works. And then there's the data lake. So you want to persist the data either as it is or close to it, after some transformation. The whole idea is you don't have to necessarily do a ton of work when the data is flowing in, but you just land it. That's the whole idea. If you have enough data coming in, you just want to get it landed somewhere so you can use it later. So you have to remember though, the bigger that the data gets, the more data that comes in, the more comp sci actually matters, right? Big O becomes important the more and more data you get. So you don't, you really start to pay attention to some of the details. So you want to fill that lake. Again, this sort of relates to what Keith was talking about, but there are short-term and long-term cases. So for short-term, I kind of like to say, this is data that's within a restricted period of time that's shorter than the period of time in which long-term data can be stored efficiently. That's kind of a weird way to say it, but basically, short-term data is data within a certain amount of time that needs to be acted upon quickly or that needs to be analyzed right away. For you to collect data that's longer term, it takes longer, it takes more effort, and it takes more time. So you need to get data in short term. So usually this is row-based, right? So a use case right here would be, temperature change chart for the last 5 minutes, right? So row-based data is easy because it's, it doesn't take much memory to create row-based data. It doesn't take as much processing power, and it's just easy to do. So here's a few examples. Avro is a format. I should probably preface this by saying that every product that I mention, if I don't say so, is Apache. So I get tired of saying Apache Avro, Apache this, Apache that. So Apache Avro is row-based, protobuf, Captain Proto, flat buffers. Some of these are more efficient than others. Some of them are more supported than others. I personally have an affinity for Avro. It's a great format, and we'll talk about why in a minute. Long-term data, this is more of the analytics. So, for example, find the top 10 hotels by water consumption per occupant in the last year. And as Keith mentioned, the ideal format for something like this is something that's columnar. So Parquet is very popular. There's others. There's one called Orc. If you're familiar with Cloudera and, what's the other one, Don? Caldera and, anyway, they're competing formats that essentially do the same thing, right? They're just columnar. And we'll talk about that, what that really means, columnar, in detail. So why Avro, right? So you can store your data in JSON, but if you get one thing out of this talk, JSON is, in some respects, inherently evil when it comes to this, right? And why? Why is it evil? Well, if you think about it, right, you're gonna store every event or message and some of its metadata with the message, which is an incredible waste, right? So, like, why do you need to store every field and the description of every field or the name of every field with that? It's difficult to parse, it's expensive to parse, it's computationally expensive to parse JSON, and it's really not tied to a schema necessarily unless you happen to enforce it. So Avro doesn't waste bytes, right? It has an encoding format that's very, very efficient. There's no row-level field metadata, and you can stuff, a lot more information into 1K of Avro than you can in 1K of JSON, even if both are compressed, right? So why is that important? Again, the bigger the data, the more comp sci really matters. So this all pertains to I/O. If you have a Spark job or Flink or some other tool that's reading this data, how long does it take to read 1K of data, and then how many records are going to be contained in that 1K of data? And that translates into real money in the end. Avro is self-describing. Each Avro file has a header that contains the schema definition used to write that file. And that's really important. We'll get to that in a minute. Schema evolution, right? So, your data changes, right? So, you add fields, maybe you delete fields, things change over time. Avro has a means to do this, so you can read Avro data with a schema that's different than the schema that was used to write the Avro data. So for example, if you add a field, maybe you want to read data that's a couple weeks old that didn't have that field, right? You can have a different schema that has that new field in it, that has a default value, so that you can read it and it'll get the default value. So that's pretty important. Avro has optional code generation. This is really convenient for clients, right? So if you have an Avro schema, which looks like this on the right-hand side here, this is in JSON format. It has like another IDL-ish kind of weird format that you can use, but this is pretty normal right here. But you can take this and you can plug it into different tools. There's like Maven has a plugin, and Gradle, and there's a bunch of other ones that you can just take this and generate, whatever, Go code or Java classes or whatever. There's a bunch of different ways to do it. And that's convenient, although it's not required. You can read Avro data without code generation. Parquet. So why Parquet? Well, Keith mentioned some of the reasons why columnar data is so important. And one of them is, if you think about it, if you're doing analytical queries, normally you don't need all of the data. You're not going to query every column. So if you only need, let's say, the temperature column and the flow rate column, and there's 10 other columns, you don't need to query the whole file, right? So Parquet files have metadata in it that tell the reader, so Spark will know, I can skip 3/4 of this file. I only need bytes from here to here, right, for these two columns. And that's so much more efficient. So that's one reason why columnar data is important. There's a predicate pushdown. So basically, what that means is things like Spark and Flink and Hive and all of these tools. If the data is encoded or written using Parquet, it knows, when it reads the data, it knows what to skip, right? So aside from just maybe you're only reading 2 columns, it knows based on values. So in Parquet file, the file knows the maximum value for this field is X and the minimum value is Y. So when Spark goes to read that file, it knows, hey, this range of whatever is not in this file. I'm just going to skip it completely. I'm not even going to read it, right? So that's one way that you can do it. And when you write your Parquet data, if you sort it properly, then you can take serious advantage of this. So for example, if you have like some field that identifies device type, right? So you have 4 devices that you use, and you only care about one of them. So maybe you can use that to have Spark skip reading 75% of your data, and that's a huge, huge advantage. So that's why Parquet is so useful. And like I said before, the column level metadata is really important. Parquet encodes all of its data in a very, very compact way. So because all the data in a single column is stored adjacent to all the other data in the same column, it can do things like dictionary encoding. So if you have a column that has, 5, 6, 10, 15 possible values, Parquet, when you write Parquet files, it figures this out. It does a little bit of analysis, and it determines, hey, there's only 15 values, right? We don't need to store the raw text or the raw value. We're going to store this in a very compact dictionary encoded format. Also, same thing with, let's say if you have times that are in there as, say, seconds since the epoch or whatever, or milliseconds, it can do delta encoding. So maybe if there's a column, there's a value, and there's another date that's maybe 0.2 seconds later than the date previously. It knows that it doesn't need to store the entire date. It only stores the difference between the two. So it's just a very, very efficient way. You can take tons and tons and tons of JSON or Avro data and store it, write it as Parquet, and it compresses down very, very nicely. In addition to the encoding, it also does regular compression. So you can do snappy compression, you can do Z-standard compression, you can do zlib, you can do all kinds of different compression codecs. So it's very, very efficient. So that's why Parquet. Flink. So Flink, there's any number of ways to ingest data, right? So you have your data coming in, maybe it's coming in through MQTT, maybe it's coming in through Kinesis, maybe it's Kafka, maybe it's Amazon SQS. It's streaming in some way, right? Flink happens to be my favorite tool for ingesting this data. And the reason I like Flink, well, there's so many different reasons, but it's one of these tools. You create pipelines and you tell it to do different transformations. You can do all kinds of crazy things. You could do, windowing and aggregation. You could join streams together. It's just super powerful. The API is very, very clean, and it's a true streaming platform. So it's not like Spark where it does like little mini batches. It's just truly streaming, and it handles state and has a great high availability story. And it's an official AWS EMR application. So EMR is Amazon's, I think they used to call it Elastic MapReduce, but I think they just call it EMR now because MapReduce is like, I don't know, is it passé? I don't know. But if you launch an EMR cluster in AWS, it's just a checkbox on the UI. Or if you're using some API to launch it or CloudFormation, it's just like a Boolean. I want Flink. And it just gives you Flink, and it's all installed, and it just works great. So it's really, really convenient. And on the right-hand side is a simple, like I guess the hello world of these types of apps is with word count, right? You'll see these everywhere. Now, I really, really don't like Scala. I really hate Scala. But this says something for Scala. This is the only language that fit on this slide. So that's probably a positive thing to say about it. That's the only positive thing I'll say about Scala. This is just the UI because everybody likes to look at the UI. You know, I'm not sure why I put it up here, but it's well done. You can get all kinds of metrics from Flink. It has a great story for that. So you can tap into JMX or whatever, you know, Prometheus or whatever tools you want to hook into Flink, and it does a really good job with that. It handles back pressure really well, and it gives a nice visual presentation as to what's going on. And it scales out really well also. It's just a matter of adding nodes to your EMR cluster. So you just pay for it, and you're good. Apache Beam. So all of these different tools, Spark, Flink, Apex, Nemo, Gear Pump, MapReduce, there's probably 10 others I can't even think of right now. They all have their own API for handling streams of data. So, you know, some of them support windowing, some of them don't. They all support roughly the same set of features. You know, usually you can join streams, you can group by, you can create group by keys and values and things like that. So this project took all the most common operations you can do and even some of the more uncommon ones, and they created like a generic API. And they allow you to plug in a runner, which is pretty amazing if you think about it. So you can go ahead and create like a nice library of functions that you can pass around to your group or your organization, or you can write these pipelines or pieces of these pipelines and choose to run them under whatever platform is supported, and there's maybe a dozen of them. So including Spark and Flink, which are the two big ones. So the API is, it's okay, it's not great, but it's not quite as intuitive as Flink. But if you think about it, you know, how long is Flink going to be around? How long is Spark going to be around in its current incantation? Like, what if it goes south, if they start breaking it? I don't know, maybe not. But this will be around for a while, right? This, I believe, is also the default API for Google Cloud Dataflow, I think. So it's just a really nice way to abstract the whole ingest pipeline. I guess the only downside really is it's a kind of a least common denominator type of approach. So sometimes it'll generate plans or graphs or steps for whatever runtime you're using, Spark or Flink or whatever, that aren't the greatest. So you have to, your mileage may vary, but they're always working on it. And it works really well. Okay, AWS Data Lake. So AWS Data Lake is, I believe it's officially called, correct me if I'm wrong, Keith, it's a solution. Is that what they call it? An AWS solution? Yeah. Probably, okay. So it's a little confusing. It's not a product per se, but all the pieces that you need to create a data lake, they exist in AWS. So somebody at Amazon had a really smart idea and decided, well, you know, why don't we just create CloudFormation templates that allow you to just spin up an entire data lake. So that's what they did. So it's really nice. They have, with Cognito, they have authorization and authentication, and in conjunction with an optional Active Directory solution if you want to plug into your company's, you know, Active Directory. They have a metadata solution with AWS Glue and DynamoDB. So all the metadata for all of your ingested data exists. They have a storage solution with S3, so that's where all your data lands. They have a search solution with Elasticsearch. With CloudWatch and CloudWatch logging, you get monitoring and metrics. And then with Athena, you get a solution for querying your data. So this is actually a really, really nice way to go. I think. And you can, since it's just a CloudFormation template, you can do whatever you want. You can change it. You can fold in pieces of your architecture. It's definitely open to what you want to do. That's, I guess that's about it, really. Thank you.